All right, so we're in section 1.2 now, still looking at the topic of limits, but this time we're taking a different approach than we did in 1.1. In the last section, we were looking at estimating limits by using both the graphical and numerical approaches. And in both of those cases, we were specific in saying that we were estimating limits because neither of those approaches are all that exact. However, in this section, we're going to be using an algebraic approach that will give us exact limits depending on what it is we're taking the limit of. So to get there, we first have to review well, it's not review, we have to go over a list of properties that limits have. Now, in a full calculus course, if this was like an engineering calculus course, we would probably take some time to prove maybe one or two of these just to show why they work. In this class, we're just going to be kind of taking them for granted. I will talk about kind of logically why the first two work, but the rest we're going to just sort of take on faith here. So let's suppose for a second that f and g are just two functions whose limits we know as x approaches c. Let's say that the limit as x approaches c of f of x is L, the limit as x approaches c of g of x is m, and L, M, and C are all assumed to be real numbers. Then we get this following list of properties for limits concerning the functions f and g. These first two properties actually don't concern the functions f and g, but the remaining 7 do. So this first one says that the limit as x approaches c of k is equal to k for any constant k. So in other words, if you're taking the limit of a constant function, it doesn't matter what x is approaching, that limit will always be exactly equal to the constant in that constant function. Property 2 says that if we're taking the limit as x approaches c of x, which is now a function of x, it's like the function y equals x, then that limit will always come out to c. In other words, the thing that I'm approaching is that limit. And the reason for these two properties we can see from these graphs down here. So this first graph right here is what the graph of a constant function looks like. This is like the graph of y equals k, where k is some constant. And in this case, my constant is 3, but we're just going to keep it kind of general and call it k. So as x approaches any number, if I put c like right there, then as I approach c from the left and as I approach it from the right, the value of any point, or the y value of any point on that line, is always the same number. It's always k. So it doesn't matter where c is. As I approach c, y is equal to k that entire time, which is the reason why the limit comes out to k. Take as a different example, this is y equals x right here, and this is for property 2. If we pick any value of c, let's say this value of c right here, then as I approach c either from the left or from the right, then we are just approaching that point on the line, okay? But because this is the line y equals x, if this x value is c, then the corresponding y value would also have to be c. And that's the reason why we get this second property here, okay? So these two are kind of easy to see why they work just by looking at the graphs of the functions that we're taking those limits of. Now, the remaining 7 properties here concern these kind of more general functions f and g, and what it is we're looking at how limits interact with different operations that we can perform on functions. We know from algebra that you can do a lot of things to combine functions. You can add 2 functions together, you can subtract them, you can multiply them by constants, you can multiply them by each other, f times g, you can divide them, take square roots of them, or nth roots of them for that matter, or to raise them to powers. There's all these different things that you can do with functions. And it turns out that when you take limits of those different ways of combining functions, the result ends up being kind of what you would expect it to be. So as an example, property 3 says if I take the limit as x approaches c of f of x plus g of x. So we're taking 2 functions and forming a new function out of them by adding them together. If we take the limit as x approaches c of that new function, the result is the same thing that we would have gotten by just taking the limit as x approaches c of f of x and adding that to the limit as x approaches c of g of x, or using the limits that we wrote up here, L plus m is what this would be equal to. Okay, we have a similar result for subtraction. Notice the limit of a difference of functions is the difference of their limits. We have a similar, well, it's kind of similar property for when you multiply a function by a scalar. A real number. We would use the term scalar in a different class, but if you multiply by some real number k. If I take a function f, multiply it by a real number k, and then I want to take the limit as x approaches c of that new function I just created, I would get the same thing as if I only took the limit as x approaches c of f of x, and then multiplied that by k. So in other words, these constant multiples can be pulled out of limits, is essentially how we're going to think of that. If I want to take the limit of a product of functions, the result is a product of those limits. If I want to take the limit of a quotient of functions, then that is the same thing as the quotient of these two individual limits. But there is a condition on this one, and it's actually a very, very important one that we'll revisit partway through this section. This limit in the denominator has to be non-zero if we're going to be using this approach. Now, at first glance, it probably makes sense why that's the case, because if this is going to be equal to L over M, then M can't be zero because otherwise you're dividing by zero. It turns out, however, that there are cases where this limit down here can be zero, and the limit of this quotient of functions will still exist, even though that denominator is equal to zero. And there's ways of determining how that's going to happen, but the way that we evaluate those limits is different than this property. So we spend some time talking about that in the latter half of this section. The last two properties basically say that limits can be brought in to powers like this. So if I have a function f of x and I raise it to some positive integer power n, then the limit as x approaches c of that new function is the same thing as if I just took the limit of f of x as x goes to c and raised that to n. And then if you notice, we have a similar property for radicals. Limits can be brought into radicals. Okay? And so we're going to be using these properties to evaluate a couple of limits. Let's take a look at some examples. Our first example is going to be a graphical one. So here we have the graph of two functions, f of x and g of x. If you can see in blue here, f of x is this thing that looks like an upside down parabola. G is like this right side up parabola, if you want to think of it in those terms. And what we want to do is find the limit of some functions as x approaches different numbers, functions that are created using f and g kind of as like ingredients. So here's how we're going to do this. Starting with this, the limit as x approaches 2 of, and then notice in square brackets I have 3 times f of x plus x times g of x. Well, one of my limit properties says that if I take the limit of a sum of two functions, that's the same thing as the limit or the sum of the limits of those functions. So I can write this as the limit as x approaches 2 of 3 times f of x plus the limit as x approaches 2 of x times g of x. So I'm using property 3, which again right here says that this limit, you can almost think of it like a distributive property, even though we don't call it that. It's almost like this limit distributes over that addition operation. Okay? But then we have a property that says if we have something times a function, whether it's a constant or another function like x, that we can bring that out. So, well, let's back that up a second. Constants can be brought out. This would be the same thing as the limit as x approaches 2 with a 3 out front of f of x plus, now this is not a constant. That x is a function in its own right. So I have to write that as the limit as x approaches 2 of just x. But we had a property that said the limit of a product of functions is the product of those limits. So I can write that this way. Okay. So at this point, I can actually start getting some values out of this, because I can evaluate all three of these limits either by using the graph or by using one of the properties in our table on the previous page. So let's start with this first one. What is the limit as x approaches 2 of f of x? I'm going to find the f of x function, which is this blue one. I'm going to find 2, and I'm going to see what is the function approaching as x approaches 2 along this curve. Well, I can see that we're approaching this point right here. And the y coordinate of that point is -3. So this limit looks like it should be -3. And in fact, we know it's -3 because it's labeled in this case. I'm not just making an educated guess. The next one, the limit as x approaches 2 of x. Well, property 2 from our table dealt with limits of that type. The limit as x approaches c of x is just c, whatever it was that x was approaching. So since x is approaching 2 here, this becomes 2. And then finally, what is the limit as x approaches 2 of g of x? Well, I go up to my graph here, I find g of x, the red parabola, and I let x approach 2, which means we're going this direction. We're approaching this hole right here. I'm not sure if you can see it very well, but that's a hole as opposed to just a normal point like we have here. But remember, it doesn't matter if there's a hole there as long as your function is approaching the same number as we go from the left and from the right. In this case, it's approaching the number 1. So that would be 1. Okay? 3 times -3 is -9. 2 times 1 is 2, and -9 plus 2 would be -7. So that's that limit. And notice all that we did is we took this kind of complicated function and used our property to break it down into these simpler pieces, which we could all evaluate without much trouble. Okay, we're going to do the same thing for part B. So here I have the limit as x approaches 0 of g of x squared over the square root of 5 minus f of x. So the first thing I can do is that property, let's see what number it was, property 7, which says that the limit of a quotient of functions is equal to the quotient of the limits of those functions. I'm going to bring the limit into the numerator and the denominator. So I'm going to write this, limit as x approaches 0 of g of x squared over the limit as x approaches 0 of the square root of 5 minus f of x. Now that property does say that we can only do that if this limit down here is not equal to 0, which it turns out it's not in this case, but we will get to showing that in just a second. Okay, the next thing I'm going to do, I'm going to use the property on the previous page that says that limits can be brought in to powers. So this is the same thing as the limit as x approaches 0 of g of x squared. So notice the limit got brought into those brackets there. Over, I can also bring limits into radicals. So this becomes the limit as x approaches 0 of 5x, oh sorry, just 5 minus f of x. Okay? So I'm putting the 5 minus f of x in parentheses because that limit law that I just used brings the limit into the entire radicand, the thing under that radical. To indicate that, I'm putting this in parentheses to show that the limit applies to the whole thing and not just the first term. But now we can use another property that allows us to bring this limit into each of these individual terms. That's property, I want to say it's property 4, where limits can be brought into differences like this. So this becomes the limit as x approaches 0 of g of x squared over the square root of the limit as x approaches 0 of 5 minus the limit as x approaches 0 of f of x. Okay, so now I have these 3 limits, all of which I can find either using the graph or one of my properties. Let's start with this top, this numerator, this limit as x goes to 0 of g of x. I'm going to go up to my graph. G of x is the red curve here, and as we approach 0, as x approaches 0, y is going to -2. So that's a -2. Right here I'm going to get -2, but don't forget that we're squaring that also. Okay, down here, the very first property on that previous page said that if you're taking the limit as x approaches any number of a constant function, you just get that constant. That's it. And then finally, minus the limit as x goes to 0 of f of x. Where is f of x? This blue parabola right here. And as we approach 0, our function is going this way. And the y-coordinate there is 1. So that would tell me that my limit is 1. Okay? -2 squared is 4. 5 minus 1 is 4, and the square root of that is 2. And so we get 4 over 2, or just 2, as an answer. Okay? Now, if you notice, that was a lot. There was a lot of steps there. And it might feel like that was overkill, and it kind of is. But it's showing how we use each of these different properties to evaluate these various limits. Now, that was using a graph. But we can do the same thing with algebraic expressions. So let's start with part A here. I want to evaluate the limit as x approaches -2 of 3x minus x plus 5. I can do the same thing. Remember, those limits can sort of distribute over both addition and subtraction. So I can write this as the limit as x approaches -2 of 3x squared minus the limit as x approaches -2 of just x plus the limit as x approaches -2 of 5. Okay? Two of these, I have properties that right away tell me what to do. We know that this one is going to be -2, and we know that this one is just going to be 5. This one requires a little extra work. So first of all, I can bring the 3 out. 3 times the limit as x approaches -2 of x squared. So that 3 comes out. We said that this limit is going to be just -2, so this is minus -2. This limit we said would just be 5, so plus 5. Okay. Now, one other thing I can do, I can take limits and bring them into powers. We saw that on the previous example. So I can write this as 3 times the limit as x approaches -2 of x squared. So the limit just got brought into that second power that's happening there. Minus -2, that's the same as plus 2, plus 5, that would be plus 7. Okay, now the limit that's in here, I know how to evaluate from property 2 in our list of properties. The number that x is approaching is what that limit's equal to. It's equal to -2. So this becomes 3 times that limit is -2. Don't forget that we're squaring that. Plus 7, that's 3 times 4, which is 12, plus 7 is 19. Okay, so that's what that would be equal to. Notice we're still using the same properties. We just don't need to refer to a graph because we can work with this algebraically. That's kind of what the name of this section is implying. Let's do one more of these, and then we're going to start looking at a faster approach to evaluating these limits without having to write all of these steps. We'll actually start looking at that in the next video. But for this one, I want to evaluate this limit. Now, this is the limit as x approaches 1 of x squared times x to the 4th plus 7 quantity to the -1/3 power. Remember, rational exponents and negative exponents, we have interpretations for those. So this x squared is just an x squared. But this down here, when I raise something to a 1/3 power, that's the same thing as a cube root. And the fact that it's negative means it's going to bump that thing down into the denominator of this quotient right here. So this is an equivalent way of writing that same expression. X squared over the cube root, that's my dog, sorry, over the cube root of x to the 4th plus 7. Okay, so that's the same thing, just written in a different way. Now, actually, let's do this. This limit can be brought up into the numerator and denominator separately. So I can write this as the limit as x approaches 1 of x squared over the limit as x approaches 1 of the cube root of x to the 4th plus 7. Using our properties, which we've now had a little practice with, so this shouldn't be too difficult. We're going to bring the limit into the power there, so this becomes the limit as x approaches 1 of x, and then I square that over, I can bring this limit into that cube root there. Limit as x approaches 1. Remember, just like that other example, we kept the stuff under the radical in parentheses because in a later step, really the next step, we'll distribute that limit into both of those. Okay, this is the same thing. Let's evaluate this one. So the limit as x approaches 1 of x, we now know from property 2 is just 1, so that becomes 1 squared over, I can distribute this limit in to the sum of terms that's appearing right here. So that becomes the limit as x approaches 1 of x to the 4th plus the limit as x approaches 1 of just 7. Almost there. Okay, 1 squared in my numerator, I know that that's just the same thing as 1. Then I have this cube root down here. We can bring limits into powers, so I can write that as the limit as x approaches 1 of x to the 4th power plus, and then we know that when we take limits of constant functions, we just get that constant back. So that's just going to be 7. Okay, finally, I need to evaluate this limit here. So I have 1 over the cube root of, now this is the limit, this is like from property 2. So the limit as x approaches 1 of x would just be that 1 there. 1 plus 7. Okay, now we have nothing but arithmetic to do. So 1 plus 7 is 8. The cube root of 8 is 2. So this becomes 1 over 2, or 1/2. All right, we're going to go ahead and end this video here. But like I said, starting in the next video, we're going to look at a much less tedious process for evaluating these limits where we don't need to do all of these steps.